When a surveillance camera gets covered, shifted, or blinded by a lighting change, every downstream analytics pipeline silently breaks. Detecting that failure without drowning in false alarms is notoriously difficult. Traditional tamper detectors rely on heavy background modeling, learned references, or per-frame comparisons that either drift over time or trigger constantly on day-night switches. This research introduces a deliberately narrow, auditable streaming state machine designed for two specific sensor faults: texture collapsing lens occlusion and abrupt photometric scene transitions. Instead of full-frame analysis, the detector samples mean luminance along every fourth column and local gradients on a quarter resolution grid, keeping arithmetic strictly bounded. It maintains a clean-only reference window. Crucially, any frame flagged as tampered is never allowed to update that baseline, preventing reference contamination. It runs two parallel decision paths: a scene transition path tracking interframe mean jumps and gradient ratios, and an occlusion path that requires a texture collapse strictly paired with a bounded luminance shift, effectively filtering out defocus or partial covers. To eliminate nuisance alarms, it applies a coarse 32 by 32 structural grid that acts as a negative gate for structured lighting, alongside explicit suppression windows for rapid brightness changes. Alarms are emitted episodically, one notification per tamper event, not per frame. On controlled sequences, the state machine achieves an F1 of 0.8, and across millions of public dataset frames, it maintains near-zero false alarms while catching in-scope faults with high recall. On commodity hardware, it processes 720p video at over 1,200 frames per second. This isn't a universal tamper classifier. It deliberately excludes pure camera rotation or subtle defocus, delegating those to registration or learned modules. But for embedded pipelines where deterministic behavior, auditable logic, and bounded compute matter, it provides a transparent, hardware-agnostic sensor health signal. If you want the exact mathematical predicates, configuration safety rules, and full evaluation protocols, the paper and supplementary material break down every constraint and public data audit in detail.